Since the first time I saw them, I've been fascinated by fractal geometry, or fractals, and to me they are a reflection of many aspects of nature. The characteristic that draws me to fractals is that they are infinitely self-similar, but always unique, much like people. A fractal is a rough or fragmented geometric shape that can be split into parts, and each part of which is at least approximately a reduced size copy of the whole, and that property is called self-similarity. Looking at fractals gives me a grasp of being infinitely large and infinitely small at the same time, yet at both scales, whole and complete. I'm on an exploration to see if fractal geometry can give us a model of workability that can be realized at any scale. Is the same process that supports one's inner journey towards finding fulfillment the same as what would be expressed outwardly at the scale of community, nation, or world? I wonder if there is something that can be taken from our personal experiences as a model that could be useful in looking at different scales of interpersonal relationships. One of the aspects I love about fractals is the feeling of play around them. The complex math involved includes an imaginary number. An imaginary number is a number that gives a negative result when it's squared. The name imaginary number was originally coined in the 17th century as a derogatory term, as such numbers were regarded by some as fictitious or useless. But today they have essential, concrete applications in a variety of scientific and related areas. The rise of computers opened up the possibility of playing more fully with mathematics. With fractals, the calculations involved are repetitive, boring, and number in the millions. To produce the Mandelbrot set on a single screen takes more than maybe 6 million calculations, even more if the iteration limit is set high to increase the detail. No human could endure the boredom, but a computer will. Computers are particularly good at mindless repetition. Computer is our telescope, our microscope, and our art gallery. So what is a fractal? It's a simple question with a very complicated and very long answer. The technical answer, while accurate, doesn't help much because it uses fractal speak and other jargon that very few people understand. So I won't try to give that definition here. The simple answer is that a fractal is a shape that when you look at a small part of it, has a similar but not necessarily identical appearance to the full shape. Take, for example, a rocky mountain. From a distance, you can see how rocky it is. Up close, the surface is very similar. Little rocks have a similar bumpy surface to big rocks and to the overall mountain. This concept of self-similarity can be a little hard to come to grips with, but it's a fundamental part of fractals. You can see in these images that smaller areas of the fractal shape look very much like the larger full-size image. And with the Mandelbrot set, you can continue this enlarging or zooming process as deeply as you like, and you'll still see the same sort of details and shapes at very tiny sizes that you see in the full-size image. This is what is meant by self-similarity. Many other fractal types get wildly different as you zoom in. They're still self-similar, but they're not rigidly self-similar. This is what makes fractal exploration so intriguing. The features that you see as you zoom are always changing, teasing you a little bit with familiarity, and maybe tantalizing you with new and unexpected twists. With just a single fractal shape, you can explore forever and never see everything that it has to offer. The further you zoom, the more likely you are seeing something that no one else has ever seen before. And with modern computers, it's very easy to zoom and zoom and zoom. With just a few clicks, you may have zoomed so far that the original fractal image in scale is larger than the sun. The Mandelbrot set is drawn in the complex plane. The complex plane consists of real numbers along the horizontal x-axis and imaginary numbers along the vertical y-axis. The value for each coordinate is determined by iterating a mathematical function. The iteration consists of computing the function repeatedly, using its previous result as new input. There are two possible outcomes for each series of iterations. The series may diverge, that is, grow without bound, further and further away from the origin, or the values of the series may stay near the origin forever. Those points whose series stay near the origins forever are the ones that are inside the Mandelbrot set, and conventionally they are colored black. Those points whose series diverge towards infinity are outside of the set. And there's a little shortcut. If at any time it can be shown that the magnitude of the calculated number is more than 2, then all successive values will be larger than the ones that came before. Therefore, we can assume a value for each coordinate equal to the number of its iterations it takes that point series to exceed the magnitude 2 limit. Points whose series exceed the magnitude 2 limit have a finite value and are outside the set. There are a number of ways to display the points outside the set, coloring them according to how quickly they escaped the magnitude 2 limit. And since we don't want to run calculations forever to find the set, we set a limit to the number of iterations. Points whose series stay within the magnitude 2 limit up to the iteration limit are colored black. The higher the iteration limit is set, the more accurately the black pixels represent the actual Mandelbrot set. All fractal color is essentially made up. There's no color inherent in fractals. It's just either in the set or out of the set. What makes up the colors is how many iterations it took to determine that the number is out of the set. The Mandelbrot set gives me some insight into the relationship of chaos and order. What appears to be chaos at one scale appears to be orderly at another scale. What is so until such time as we give it language and superimpose that language over what is so. At that time, what is so is collapsed into the language that we superimpose, giving us such things as order or chaos. The natural world has always had a chaotic way about it. The mathematical world has always had amazing complexity resulting from simple equations. So why has chaos theory just evolved as a critical part of science, mathematics, art, and the computing world? The simple answer is computers. The calculations involved with fractals are repetitive, boring, and number into the millions or billions. To produce the Mandelbrot set on a single screen takes maybe over 6 million calculations. No human would be stupid enough to endure the boredom, but a computer will. Computers are particularly good at mindless repetition, and the computer is our telescope, our microscope, and our art gallery. We really can't explore chaos without it, and we certainly can't produce fractals without computers. But it is necessary to use the computer as an investigative tool. Most computer use is based on putting in data and instructing the computer on what output is required. Chaos theory arose as scientists and mathematicians started to play. To put in numbers and watch as they careened around this plane, mostly in the complex plane, and they produced detailed patterns. They watched as the computer produced the numbers and didn't just wait for the final result. They tried different ways of plotting and exploring the equations, mostly for the fun of it. Playing with mathematics, science, and computer programming produced images which looked like nature, ferns and clouds and mountains and bacteria. They indicated why we can't predict the weather. They seemed to match the behavior of the stock market and populations and chemical reactions all at the same time. Their investigation suggested answers to questions which had been asked for centuries. Things like about the flow of fluids as they move from a smooth to a turbulent flow, about the formation of snowflakes, about the swing of a pendulum under the influence of magnets, about the tides and heartbeats and cauliflower and rock formation, all kinds of things that show up in nature. basic technique of these fractals can actually be explained without resorting to confusing mathematical used in fractal creation. Some interesting things happen. Sometimes the number you get by feeding the results of a formula back into the formula, also called iterating, explode into enormous numbers that just keep getting bigger and bigger. Those points get colored one way. At other times, the numbers home in on a number, getting closer and closer to it. They get colored a different way. Calculating fractals this way takes a lot of work. A small fractal image, even like a computer screen, has over 300,000 points. Each of these points might require running a number through the fractal formula more than 1,000 times. This means that the formula has to be computed more than 300 million times, and that's a pretty mild example. Extreme images, such as poster-sized fractals, can involve more than 1 trillion calculations. Fortunately for the impatient among us, modern computers are fast enough to do the job in a few minutes. Large fractals may take hours or days, but exploring fractals has never been easier. As I stated at the outset, fractals are a huge topic. All I've even talked about here is one particular type of fractal, escape time fractals, but there are many other types as well. Unfortunately, the further you look into fractals, the more math you'll need to know. There are very few fractal-related books or web pages that don't get very heavily into mathematics. I've attempted to assemble these thoughts to kind of give you an explanation of fractals in an accessible way, but there's no hiding from the fact that underlying it all is math. The Mandelbrot set is drawn in the complex plane.